all of yourselves. Hey, how's it going, everyone? Good to see you all. How are you on this fine Tuesday morning? I'm pretty good, you guys. I'm pretty good. I had a nice breakfast of pancakes with blueberries in them. It was kind of good. I had a great time. Did anyone get to see? I posted on Classroom late last night. Sorry it was late. The video sort of summary for this unit. I'm sure no one's had a chance to watch it yet because it was really late and it's still kind of early, but it is up there. If you could watch that video by next class, that would be great. It's something like 15 or 20 minutes, but it really goes through everything we need to know for at least this week and this homework, the really short homework that I gave you, which is also up on our Classroom, if you'll check. It's just 2 questions. There's a couple parts to each question, but I tried to make them as short as possible. And more than just as short as possible, I tried to make them substantive, not like busy work, because I hate busy work, and I'm sure you guys do too. So I tried to make them actually useful questions that will actually help you understand material and practice. So, everyone is on. I think everyone's on Classroom, right? We're all there, pretty much. And you've all seen that stuff, I hope. Oh, there's also I can't call it an assignment because I'm not requiring it. But if you would like to do some extra reading in the textbook, I think I put it up in as an assignment as well. Not an assignment, just on our post in Classroom. It's chapter 2.2, and mostly it's chapter 2.3. Some useful stuff in there. So not to really get ahead of myself too terribly much, but I did want to take you guys through some of the stuff that I was talking about in that particular video. And I'm hoping there will be plenty of questions. I especially wanted to take you through the experiments that we talked about the other day. I guess there's 3 experiments I want to talk about. And let me find my notes here. I seem to have lost my class notes. They're coming back up. There they are. Hey, look. There they are, right where I left them. Who would have guessed? So if we have, hopefully, everyone has whatever their preferred note-taking device is, whether it be computer or whatnot, out. We're gonna do some quick notes here. Hopefully not too much for you. And I'm going to try to do some drawings, because I think diagrams actually really help with this kind of stuff. I think diagrams are super helpful. So, let's try it. Just managing my screen here. There we go. There we go. Okay, I can actually see all of you. Hooray. And there's that. Okay, so we talked about a bunch of experiments last class. There are 3 in particular that I want to go into more detail about how they actually work, because I think the science behind it is really interesting. So, the first one, I mentioned Thomson discovered the electron. Some of his experiments were in the late 1800s. I think he won the Nobel Prize in 1897 or something like that. And his atomic theory, we mentioned 1904 was his publications on that. So I wanted to talk a little bit about the publication, the experiment that he actually did to discover the electron. He used something that's called a cathode ray tube. CRT. Does anyone remember these? I am old enough to remember televisions that worked on cathode ray tubes. They're like huge and bulky. They're shaped like, I don't know, kind of like a big funnel almost. There's like the back of the TV, and there's this like huge, incredibly heavy thing, and then there's like this curved screen that they have. And when I was a kid, probably younger than you guys, because I think LEDs and more modern technology started coming in when I was still a kid. Big TVs were, and I mean really any TV was kind of shaped like this, and they were just insanely heavy. They were just stupid. So I'm kind of glad that we have our modern LED technology, and OLED is the newest stuff, right? And actually, LEDs, I should mention, LEDs are based on quantum mechanics. They work on principles of quantum mechanics, which is kind of cool, I think. It's like an everyday application of quantum. But this is how TVs used to work. The really super basic way to describe it is that you have, I guess you'd call them two charged poles. This guy would be a cathode, and this guy would be called an anode. This guy's negatively charged, and this guy's positively charged. And you have it set up in such a way that electrons, and everyone knows electrons are blue because, of course, arbitrary decision. Electrons get fired out of the cathode towards the anode. They're repelled by the negative charge, and they're attracted by the positive charge, so they're accelerated very fast. And what comes out of this cathode and anode is what they used to call cathode rays, which really are just fast-moving electrons. Well, they called it cathode rays because they didn't know about electrons back then. And so what Thomson did, this is J.J. Thomson in the late 1800s. I think there's no H in his name, if I remember correctly. No, there is. I'm sorry. Thomson. That's it. J.J. Thomson. So the experiment Thomson did, and there's actually a really nice diagram of this in our textbook. I think it's chapter 2.2. Is he set up, after these cathode rays are coming out, he set up a magnet with two poles on either side of where the rays are going. So maybe there's a north pole and a south pole, and the rays go in between the magnet. And on the top and bottom, he set up, I'll do it in red here. On the top and bottom, he set up these charged plates that have electrical charge on them. I think the diagram in the book says that the positive plate was on the top and the negative plate was on the bottom. I don't know if it really matters what the arrangement is. But what he found is that when he fires these cathode rays through this setup, and he can tune the amount of charge on these plates, he sees them deflect to various angles based on how much charge he puts on those plates. And he would measure it. There's like a glass, this is all in a glass vacuum chamber, it's all in a vacuum. On the end of the vacuum chamber here, he has a really finely graded scale, like basically a tiny ruler, and it's got fluorescent dye on it. So when an electron at high energy hits it, it makes it light up. Kind of like those little light sticks that you set out in the sun, and they glow for like 15 minutes or something like that. That's fluorescent. It's just the energy from the light gets absorbed and then re-released. This is the same thing. It fluoresces, and he can tell how much it deflected. And by being really careful about measuring, first of all, measuring the amount of charge on these two plates, and then where it deflects to, he was able to measure the charge to mass ratio of the electron. So take the charge, divide it by the mass of the electron, and he was able to measure that. So that was the discovery of the electron, these little particles that have a negative charge and have some mass. He wasn't able to figure out the charge or the mass individually, but he was able to find out their ratio. And it's that ratio because if they had a larger mass, they would be deflected less. But at the same time, if they had a smaller charge, they would also be deflected less. So these kind of things are, these two quantities are not separable from this experiment. But it took a slightly later experiment, one of my all-time favorite physics experiments, to figure out the charge of the electron, and therefore, once you have the charge to mass ratio and the charge, you can figure out the mass through some simple algebra. It's called the Millikan oil drop. I love this experiment. I was lucky enough that I got to do this experiment when I was in college. I had an advanced lab course that had an apparatus for us to do this. I wish I could have one for you guys to do, but it's like thousands and thousands of dollars to get a good one that actually works. So what Millikan had, and I'm going to spell his name for you. Millikan oil drop is what the experiment is called. And weird trivia. When I was teaching in Hawaii, one of my colleagues was related to Millikan. She was, I think her name was Sarah Millikan, which is kind of cool. I think she was like his great-granddaughter or something like that. So Millikan had a bunch of oil, and he had a little thing that misted. Christian asks if I will post my notes on Classroom. Yes. The only reason I have not yet is because I've been insanely busy with other stuff. But I will post all these, and actually I will try to post the recordings of my video here as well on my YouTube channel and put them on Classroom for you guys. I apologize that they're not up yet. Things have been taking longer than I expected, which is kind of stupid because I should have expected it. So anyway, Millikan has this oil, and he has a special little machine that it's what called atomizes it. It doesn't make it into atoms. It makes it into like tiny droplets. And these droplets he projects into this kind of big cylinder vacuum chamber. Cylindrical vacuum chamber. On the top here, and these are tiny, like really tiny oil, like almost microscopic oil droplets. On the top, what you see is he has a plate here. A plate that he charges. I think it's negatively charged, if I'm remembering correctly. And on the bottom, you know what? I might be wrong about that. Yeah, it has to be the other way around. I apologize. It's a positively charged plate on the top. My apologies. Hold on. It's early enough in the morning and I have not had my coffee. Let me think about this for just a second before I tell you the wrong thing. No, I was right the first time. Darn it, I was right the first time. It's a negatively charged plate on the top. I always use blue for negative and red for positive. There is absolutely no reason why other than the fact that I just kind of like those colors for negative and positive. It's kind of silly. Okay. So there's a negatively charged plate on the top and a positively charged plate on the bottom, and he can tune the amount of charge with a little, like a dial, basically, turning it back and forth, like a radio dial. And in the top plate, he has this little hole in the middle that oil drops here can fall through. So they fall through in this little stream of drops. And he can charge, the most important part, what color do you guys think X-rays should be? Maybe bright green, because it's kind of horrible. He shoots some X-rays at these oil drops. And what this does is it actually knocks some electrons, maybe 1 or 2 or 10, whatever, off of each oil drop. Which means that the oil drop goes from being neutrally charged, from zero net charge, to having a positive charge, because the electrons have left and there's protons left over. Or at least a couple of the electrons have left. And so then they have these positively charged drops, and he's able to tune these plates for each drop. He's able to turn his little dial for the charge on these plates and get individual drops to hover, because he's balancing the electric force. So if it's a positively charged drop, this positively charged plate is repelling it, and this negatively charged plate is attracting it. And he can tune it perfectly, the charge on the plates, to just balance the gravity and the electrical force on these drops. So he measures a bunch of these. And what he realizes, and I guess the most important part is how you observe this, he has a little microscope that looks in at these drops. So he's watching these drops through a little microscope he can look through. And maybe here's his eyes. He has nice eyelashes. And he actually has like a little graded, little ruler there to see where they stop. and how they stop. Okay, so being very careful, he notices that the amount of charge that has left the each oil drop when he hits it with X-rays only comes in multiples of a very particular number. It's 1.602 times 10 to the negative 19 coulombs, and I should introduce this unit. Coulombs are the unit of charge. They're the SI basic unit of charge. And he notices that this, there are differences in the charges of the drops. Like every drop has a different electrical charge needed to balance it. But no matter what he does, it always comes in multiples of this number. No matter what. And so he concludes that the charge of an electron is always this number, or really it would be negative this number. And he calls this the elementary charge. And it's basically the fundamental unit of charge. It's undivisible. Well, technically it's dividable. If you get really into quantum physics, the particles that make up a proton and a neutron have either plus 2/3 or minus 1/3 elementary charge, but not important. They don't exist outside of protons and neutrons, so you'll never find anything less than 1 elementary charge living in the natural world. We usually call it E for elementary charge, which is confusing because electron is also E. For electron, I always have the E, like sort of superscript to the minus. That'll always be electron. Whereas elementary charge is this, and often we'll either list a plus or a minus elementary charge. So a nice thing is that an electron has a minus elementary charge, whereas a proton has a plus elementary charge. And a neutron is 0, of course. It's neutral. So I love this experiment. I got to do it when I was in college, and if you ever get the chance to take like an advanced lab course in physics, do it, and boy, it was interesting. I probably also got to do this one. I don't remember the Thomson experiment. It's pretty easy to set up, actually. But yeah, the next experiment, I don't think I ever got to do. I'm going to show you, and this is the last experiment I want to go over today. It's the Rutherford gold foil experiment. Ernst Rutherford. And this is what proves that an atom has a nucleus, and it's not just a cloud of positive charge sitting around with electrons inside of it. Remember, that was the difference between the plum pudding model, the old one, and Rutherford's nucleus model of the atom. So what Rutherford did is he got a hold of some radioactive material. I'm not even sure what it was, to be honest. We'll just draw a little guy there. Some radioactive material that's radiating energetic particles, alpha particles, which are basically just helium nucleus, 2 protons and 2 neutrons, in all directions. And he encases it in lead. Good idea, because the lead absorbs all the radiation. Except he makes this little cave kind of thing where the radiation only comes out in this little narrow direction, right? So it's only coming out here. So he makes a ray, just like a beam of radiation. And there's another diagram of this in our textbook. And he has, just like Thomson had, he has this screen, or maybe it's glass, with fluorescence painted on it. So this fluorescent dye that when an energetic particle hits it, it lights up. So this screen goes all the way around. And in the middle of this, he puts a very thin thing of gold foil. And what you would expect if the atom was made up of just a soup of positive charge and then a bunch of negative charge, is what you would expect is that all the particles would go straight through and land directly back here on the back, and make a nice bright spot right on the back of the fluorescent screen. What he actually saw was that some of them do, but others get deflected a little bit. And rarely, every once in a while, one will bounce off and come back and kind of hit the screen way back here. pretty rare, but it does happen. And he was like blown away by this. I think the textbook has a quote from him about like how crazy he thought this was, that it actually bounced off. It was like how unlikely it was. There's also something, I forget what, there's a recording. So the textbook has a link. I think it's in chapter 2.2. And it says like, here a link of, it's one of these three guys that I've been talking about, talk about the atom. And it's like recorded in the 1920s, I think. But I recommend going to that link. You have to click through a few pages to get to the actual recording. But that recording is crazy. He sounds, I forget who it is, but he sounds crazy. Yes, Alex, we do have textbooks. It's in the syllabus, and it's online. It's free, thankfully, and it's the actual physical version of this textbook is so darn heavy, I did not want you guys to carry it around, so you can always get it online. But the link to it is in the syllabus, if you go ahead and read that. So yeah, here's the Rutherford gold foil experiment. I want to show you, really quickly, an interactive thing. Here we go. So this is an interactive, again, I think this is linked in our textbook, that shows the two different models of the atom with this Rutherford experiment. So the older model, the plum pudding, which just has like a cloud of positive charge with electrons in it. Here's your alpha particles, your basically helium nucleus, that is going to hit this gold foil, and we're going to see the microscopic view of what's going on. If this is how atoms worked, they would basically just pass straight through, and nothing would happen, right? Unbelievably boring. At least to me it seems unbelievably boring. But if we have a nucleus in the atom, we see quite different behavior. So I think, I cannot remember for the life of me, I think they have this set to gold, but I could be wrong. It might be something else. And we're going to have traces, because it's nice to see the tracks of these particles. So these guys are coming, when they come near the nucleus, you're going to see them bend their paths, because the electrical forces going on. And this is what Rutherford saw. He saw, he saw a lot of them going straight through or getting deflected a little bit, but every once in a while, you'll see one like that guy deflect backwards, which is, blew his 1897 or 1904 or whatever it was mind. Just the idea that there were these very dense concentrations of positive charge at the center of atoms. Incredibly small as well. And we can play with all these sliders. If you give the particles more energy, that means they're basically moving faster, and they're deflected less. There's less deflection. You can see they're kind of shallower angles. But if you give them really low energy, the deflections kind of have more of an effect, and you can see they're spreading out a bit more. Like these guys are going backwards there. And likewise, if you up the amount of protons, you'll see the electric force is going to be bigger. So the deflections. Say again?
Kind of like gravity?
Yeah, kind of like gravity, very much so. I don't think the neutrons have any effect, as far as I can remember. They shouldn't. So if you want to get the maximum number of deflections, right, you turn the energy way down, you turn all the protons all the way up. By the way, 100 protons in something is like, it's not a stable element. It doesn't exist very long. Uranium is 92, and it's the heaviest sort of semi-stable element that exists. So 100 is, I don't know, something crazy like Einsteinium or something like that. Around there. One of the lanthanide or actinide series. Okay, and then we can take a look at the microscopic version of this. I should turn this back to something normal. Hey, how about uranium nucleus? So as they're coming in, they get bent, their paths get bent away by the electrical forces that are going on. Okay. Whew. So, if you want to, you can go play with that particular guy there. That's all in the textbook. I have the textbook up here. Let me show you guys just because. Alexander, you were asking about if we have a textbook. And yes, here it is. So yeah, here's some diagrams. This is a cathode ray experiment. Here's the Millikan oil drop. Ooh, a very nice diagram. Here's the Rutherford gold foil. Somewhere in here is that link I talked about, which here we go. It's Thomson, J.J. Thomson. Boy, his voice is crazy. Like, I had to listen to it like twice because I could not believe he sounded so nuts. It's like a cartoon voice. And you have to click through a bunch of stuff. I'll let you do that on your own time if you like. So yeah, that's our textbook. Any questions so far, guys? How you feeling about it? All right. Oh, excuse me. So, I guess we talked just a little bit about the Coulomb as a unit. Coulomb. It's named after some old dead white dude I don't really care about. But it is the fundamental SI unit of charge. It's not actually a fundamental unit. I guess last year, the IUPAC, I forget what that's, it's some international science advisory board, redefined the base SI units. So there's 7 of them. The second for time, the meter for length, kilogram for mass, things like that. And Coulomb is not one of them. It's based on 2 others. It's based on amps, which is a unit of electrical current, like you have running through your wall, and time, seconds, basically. So 1 Coulomb is 1 amp per second, per 1 second. Just a really basic definition of what that is. So every other unit is supposed to be built up from those 7, whatever they are, the 7 fundamental units. There's amps for electrical current. There's I think lumens or maybe candela for brightness of something. There's a bunch. The Kelvin for temperature, things like that. So we've talked about the Coulomb. We talked about fundamental charges. Other properties of atoms. Oh, I suppose there's also mass is pretty important. I'm going to try my best to follow what our textbook does. I think it likes to use grams. I've been trained throughout my entire education to use kilograms instead of grams. So I'm going to do my very best to do the conversion in my head. It's not that hard for me, but I will forget sometimes. So just keep an eye on my my mistakes, because I'm going to make plenty of them, I assure you. But yeah, I'm going to try to stick with grams, which is, I think, what our textbook likes to use. There's also this idea called the atomic mass unit, the AMU. And it's a really tricky unit. I tried for quite a while yesterday and over the weekend to figure out a really good explanation of what the AMU is and how it came about. And it has a tricky history. It's been redefined 3 or 4 times. Today, it is defined as exactly 1/12 of the mass of a carbon-12 atom, which is a particular type of carbon atom. It has 6 neutrons and 6 protons, so there's 12 things inside of it. The problem is that if you calculate it that way, a proton has not 1 atomic mass unit, but 1.00727 atomic mass units, and a neutron is 1.00866, a little bit heavier. So it's not exactly integer numbers, which to me it feels like it defeats the entire purpose of trying to standardize it. Like, why not make a proton exactly 1 atomic mass unit? I don't know why. And it's definitely annoying to me. It's close enough to 1 that it makes a little bit of a difference, but really not that much. We're talking about 1% about in terms of errors. But that unit does exist, the atomic mass unit, and it's way more useful, I think, to use AMUs rather than grams, especially when we're talking about atoms. When we're talking about chemical compounds and doing chemical reactions, obviously grams makes plenty of sense because it's a unit we can see and interact with. But when we're talking about an individual atom, with a proton having a mass of 1.00727 AMU, that's easier to talk about than having a mass of 1.68 times 10 to the negative 24 grams. It's insanely small. So, just know that the AMU is a thing that exists. There are problems with how it works. It's something called the mass defect. And I sure don't want to get into that right now. It has to do with relativity and trading energy from matter to energy, E equals mc squared kind of stuff. And it's, way outside the scope of this class. Okay, so I guess since we're talking about atoms and even elements now, I guess it would be a good time to just take a first, and probably this is not your first, but take a first look for this class at the periodic table, which is absolutely lovely. I did a bunch of research over the weekend, and I found an awesome website. I spent literally hours playing with this website over the weekend, which is something only like a science nerd like me would do, spending hours playing with a periodic table website. But man, I am totally in love with it. I think it's the coolest thing ever. But let's talk about how to read the periodic table a little bit. I'm sure you're all familiar with this, but just good to have a little review. The thing that stands out the most on the periodic table is these element symbols, I guess the abbreviations, like big H for hydrogen, or P for phosphorus, or Ru for ruthenium, right? Most of these are pretty self-explanatory. There's a couple that are a little weird. These are usually like the elements that were known in ancient times, like gold, Au, I think it's like auricum, and I don't know what mercury, where Hg comes from. It's probably something Latin, like all of these. Pb is for lead is plumbum. I think the Romans used lead as plumbing pipes, so that's where that comes from. And there's a couple like tin and antimony are both weird. So there's a couple scattered around here that have weird abbreviations because they were known in ancient times, and those names come from Latin or Greek or something, maybe Arabic, something like that. Most of them, though, have pretty sensible abbreviations. Thankfully for us, on this particular periodic table, we have the names right below it, so it's easier to look up. And below the name there, it's showing us the average atomic weight in AMU of each of these elements. So on average, hydrogen is 1.008 AMUs for a hydrogen atom, which is just a little bit more than a one single proton by itself, right? It was 1.007 something. And that's because this weight is actually an average of, theoretically, all the hydrogen in the universe. If you take all the hydrogen in the universe and average the weight of them, they're going to have an average weight of 1.008 AMU, which means that there's a couple of hydrogen atoms out there, not very many, that are a little bit heavier. And we're going to get to exactly what that means. I'm sure you guys have a clue. But there's all these really cool tabs up here. I mean, the first one, it'll take you to the Wikipedia article, which is useful in and of itself. Yttrium, there you go. Here's a spectrum of yttrium. Pretty nice. The properties one is kind of where I spent most of my time because there's all of these different properties of each element that you can go through. Most of these we're not going to need this year, I think. I don't think we're going to get to like the specific heat of vaporization or fusion. Oh, we might, honestly. It depends how deeply get into thermodynamics this year. I love this one, the universe, or the abundance one. So this one, the way I have it selected here, the universe, this tells me what percentage of the universe is made up of any particular element here. So it tells me 75% of the universe is hydrogen down here, and 23% is helium. Kind of a cool note, if you look at the things that are like larger numbers, like lithium and beryllium are tiny, 10 to the negative 7% of the universe. But carbon at 0.5%, nitrogen at 0.1%, and oxygen 1%, and I suppose also neon at 0.13%. Those are pretty common elements. If you look at what makes us, it's hydrogen, carbon, nitrogen, and oxygen. That's pretty much what makes us up entirely. There's probably trace elements of other stuff, but like the vast majority of living things are made of those four things, and they're most of the universe between them. I mean, helium Helium's off doing its own thing. It doesn't really like to play with other elements. And the reason that these are the most common things in the universe is that they are made inside of stars. So the process of fusion in a star takes hydrogen and makes it into helium a lot, and then a little bit of carbon, nitrogen, oxygen, some neon, sodium, magnesium a bit, and the next biggest one is iron there, and the rest are very, very small amounts. So yeah, the stuff that's made in stars are these really common elements, and it's products of stellar fusion, which is cool, I think. And you can go through all these different options. If you want the solar system abundance, you can go there. In a meteor, the Earth's crust, the ocean of the Earth. In a human, there you go. 61% of a human is oxygen, 10% is hydrogen. Yeah, all sorts of stuff going on. I also like this discovered little tab. It shows you when each element was discovered. You have a slider, and it'll light up when it was discovered. So there's a few actually that are really new. Like Tennessean and Ognet. I have no idea how to pronounce that. Oganesson. Yeah, 2010 is when the last one was discovered. These guys down here are really new. They were discovered in these years, but they weren't given names until even more recently. I just think it's kind of cool that we now have the entire row of the periodic table like completed. I just think it's kind of nice. And if we discover a more heavy element than Oganesson, it would go down below francium here. It would be 119. And I will say that pretty much all of these guys, these really heavy guys, everything heavier than uranium actually, neptunium, plutonium, all these are very unstable and extremely radioactive, kind of like uranium. Yeah, so they are kind of ugly. Speaking of which, the theoretical 119, if we ever figure out how to put it together, not only would it be unbelievably radioactive and dangerous in that way, this particular row of the periodic table is, I would say, pretty explosive. Anyone seen a video of throwing sodium into water, like a pond or something like that? We can even look it up here. I can look at one up for you. It's kind of fun to see. If we were in person, I would totally throw a chunk of sodium into the pond and we would have a nice explosion. Potassium is even more reactive, and the further down you go, the more explosive it gets. So francium down here is radioactive and extremely explosive if it comes in contact with just about anything. Yeah?
My great uncle used to work in a lab. One time he got into this like beef war with his neighbor, and his neighbor had a pool, and for some reason he got mad.
Oh God.
And one night he just brought a block of sodium home from his work. In the middle of the night, shucked it into his neighbor's pool, and a huge explosion went off, and like the bomb squad was there and everything. Like the shingles of the roof fell off. Yeah.
Uh-huh.
Would have been like crazy.
Yeah, that's exactly right. Sodium does that, and potassium, I've seen potassium do this, is even more explosive. It's like even crazy. So a chunk of sodium like this big, and sodium's like this dull, sort of grayish metal. Like a chunk of it like this big will make a pretty big explosion. A potassium chunk like a little one like that big will make a same size explosion. It's crazy. And the further down you go on the table on this row, the more explosive it gets. So whatever 119 would be not only unbelievably radioactive and dangerous, it would also pretty much explode on contact with just about anything. So whatever it is, it's going to be some ugly stuff. I mean, francium itself is already incredibly dangerous, and it doesn't stick around very long, to be honest. Do we have half-life here? No, it's not on one of these. It would probably be on isotopes. So yeah, this first column is kind of fun. They're fun to play with, and fun to play with safely, so you keep all your fingers and toes, right, and eyes and things like that. The orbitals tab here, we're not going to worry about at all, other than like it looks pretty cool. This is some crazy quantum mechanics stuff. Look, there's Einsteinium. I think the Einsteinium orbital up there looks awesome. Looks like some futuristic spaceship. Oh, and there was 100. Remember before when I said 100 protons was like maybe Einsteinium? I was one off. It's fermium. That's fine. Hey, named after one of my favorite scientists, Enrico Fermi. That's cool. Anyway, we don't need to worry about this particular tab. It's super neat for a giant nerd like me. I love it, but totally unnecessary for us in this class. We might get into SPDF, what these mean, later in the class, though. This is what I wanted to get to today: isotopes. So you'll see in my video I did for you guys, I'll explain isotopes in much more detail there. But essentially, elements are defined by the number of protons they have in their nucleus, and the number of neutrons can vary a lot. So like hydrogen has one proton in its nucleus, and it has a couple of different versions of hydrogen with different numbers of neutrons. And most hydrogen in the universe has no neutrons at all. It's just a single bare proton. It actually has a special name called protium. If we click on this here, there it is, protium, which has just one proton and no neutrons. It's just a single nucleon up there. And 99.9885% of the hydrogen in the universe, there it is protium, just a single proton and nothing else. And it's stable. It's kind of the building blocks of everything. Like we saw before, it's about 75% of the entire universe is just a single proton. You can't get much more simple than that. But there are some types of hydrogen. There's one particular type which has one proton and one neutron. So it has two things in its nucleus and one proton. And that's called deuterium. It's as it says here, it's 0.0115% of the hydrogen that exists in the universe. Anyone heard of heavy water? It occurs naturally. There's some in the oceans. Heavy water is water that has deuterium for its hydrogen rather than regular one proton hydrogen. It's just a little bit heavier than normal water. It's an interesting thing. Deuterium is also stable. It's pretty rare, but it's stable, and so it sticks around. Then there's this other one, tritium, which has two neutrons and one proton, so three things in its nucleus, and it's very rare. Although it says 0%, but it's a very small percentage of the hydrogen in the universe. It has a half-life of 12.32 years, meaning that in 12.32 years, about half of it radioactively decays into some other type of hydrogen, one of these other two. And I have some tritium, actually. I'd have to go find where my keys are. It's a little bit of a keychain thing that I have. And because it's very slightly radioactive, it's not dangerous radioactive, thankfully, it actually glows just a little bit. And it saved my butt on a lot of occasions. It glows, and I can actually find my keys when I drop them somewhere behind a couch or in the dark or something like that. It always glows, and it should be glowing for, pretty brightly for at least 12 years. And I got it, 3 or 4 years ago, something like that. So I've got a good another 8 years before I might need to replace it. These little vials. When we're in person, I'll show you, and it's nice. It's not the kind of radiation that you need to be worried about. It's so low energy that like a millimeter of air will take away any of the dangerous radiation, or even like the top layer of your skin. If you put it up against yourself, you'd be fine. It's not dangerous, but it is kind of cool. I have the little radioactive element I carry around with me at most times. In this lighting here with my big window, you would not be able to see any of the light, but it works perfectly in the dark. So that's why I use it. Yeah. If you want to see, so these are the three these two are stable isotopes of hydrogen. This guy is kind of stable. It sticks around for a while, but if there's a lot more, it goes up to 6 neutrons and one proton here. And I don't even know what this is called. I don't even know if it has a name. It is not stable at all. It stays around for 2.3 times 10 to the negative 11 picoseconds. So picoseconds is already like, what is that SI prefix? Like 10 to the minus 15? Anyone remember that from middle school? I don't even remember it. It's tiny. But it's 10 to the minus 11 picoseconds. So we're talking like 10 to the minus 20 or 30 seconds. Unbelievably short amount of time. So it basically does not exist. If you try to assemble it, like maybe in a particle accelerator and just smash everything together, it's going to instantly decay. It'll just instantly decay into some other more stable form of hydrogen. And the rest of these guys here have, similar decay times. This guy 10 to the minus 11, whereas these are 10 to the minus 10. So, they're about 10 times. They stick around about 10 times longer, which at this time scale, even 10 times longer is basically nothing. Actually, there is a theory. There's this really weird theory that hydrogen itself decays. That a proton just by itself will eventually, given enough time, just evaporate into pure energy. It's still a theory because we've never been able to observe it like actually happen in the wild. And that's probably because it takes like hundreds of thousands to millions of times longer than the age of the universe for it to even happen once. So the decay of a proton is not something we need to really worry about. But it theoretically could happen, which is kind of interesting. It would mean that eventually the entire universe, after, 10 to the 50 years or whatever, would have no matter, no stuff left in it, just pure energy floating around. I don't know. I think it's interesting. Question?
Where do the extra neutrons go when they decay?
Oh, so some of them, that's a really good question. Sometimes, based on, these guys here are the types of decay that these isotopes undergo. Some of them, the neutrons fly off and they become sort of free neutrons by themselves. Others of them, they decay into other particles like an electron and a neutrino and a bit of light. They can sort of split into other types of particles, or sometimes it just comes out as pure energy, or light, I guess, would be that version of it. There's a lot of different ways for them to decay. As you can see here, they have 7, and then this one is stable. And I don't know. I haven't planned out that far if we're going to get to talk about types of nuclear decay. It's a pretty advanced topic. I first really saw a good treatment in a class of nuclear decay when I was, halfway through a physics major in college. So I'm not sure we need to get into it because it gets pretty crazy and pretty hairy in terms of math. So I'm not sure we really want to get into that, but it is something we could talk about. And there's a ton of different isotopes of all these different elements. The other version, they don't have this here obviously because it's a bit more variable. So if we're defining our elements based on the number of protons in the nucleus, which is this atomic number up here in the top left corner of all these boxes, you could also, other than varying the number of neutrons for isotopes, you can vary the number of electrons to get what are called ions. And they're positive ions where you've lost electrons, and they're negative ions where you've gained electrons. That's an entirely other sort of subject. I cover it a little bit in the video, and we're going to do a lot more with ions. And we have like a few minutes left just to really quickly summarize the last thing here. The last tab here, compounds. I genuinely don't know how useful this is, but it tells us that it shows the number of compounds that we know of that each element is part of. So for hydrogen, we know of 40,796 compounds it's part of. And then you click on it and give you a whole list of 40,000, 40,000 compounds. Some of them get pretty crazy, like with these interesting chemical formulas. 2,3,3-trimethyl-1-butene. Whoever knows what that is. There's a lot of them, for hydrogen especially. Other elements, like helium. Helium only exists by itself, basically. It doesn't form compounds. He's kind of snobby, like that. Let's see. I'm trying to look for sodium. Sodium forms, see, it says 803 matches. Magnesium, I guess you can click on multiples to see how many matches they form with each other, which is kind of cool. So, for example, if we're in class and we're doing an experiment and you've got, sodium likes to react with stuff, and chlorine, NaCl. Anyone know what that is?
Salt.
Yeah, just common table salt, basically. There it is. And there are, according to this thing, there are 51 things that have both sodium and chlorine in them. Obviously, the most simple is just NaCl. But you can go down here to some really interesting stuff. Sodium dichloroacetate, and it takes you to the Wikipedia article for that particular compound. I don't know. I think it's interesting. I don't know how useful this particular tab would be, but there you go. If we go back to the start, any questions about this? I'm sure you guys have seen the periodic table before, and I'm sure most of this is review to you. How are we feeling about chemistry so far? Just a quick check-in. All right. I know, we got some... Yeah, I'm okay with that. All right. Well, guys, so I guess for next class, which is what, Friday? Go ahead and watch that video I put up. I think it's uploaded by now. There were some problems with actually uploading it, so it got up later than I thought it should have. But I think it's up by now. It's not too long. Write down any questions you have. There are, I think, 2 homework problems up on Classroom. You don't need to print them out. I would say do the work on a separate sheet of paper, or even type up the work if you can do it really cleanly. If it looks nice, go ahead and type it up. But I would actually prefer if you hand wrote it and then like took a picture or scanned it in and turned it in on Classroom. I made it due at the start of class next week. So it would be the start of this class. Tuesday at, 10:15, I guess, is when our class starts. So you'd have basically a week to do it. And I was going back and forth on whether I wanted to give you the option to have the weekend to do it, or if I wanted to make it due on Friday afternoons or evenings so that you wouldn't have to worry about doing homework over a weekend. I figured if you guys wanted to just have a weekend free not to do homework, you could do it early, and I'd give you the extra time, because who doesn't want extra time, right? All right, that's it. If there's nothing else from you guys, you are free to go to a lunch, I guess, right?
Thank you.
Can I just ask you a question?
Oh yeah, sure. I'll stick around.
Thank you.
Thank you.
See you guys.